So let's start with this introduction to the tensorial group field theory framework for quantum gravity. The intention is to give you a brief overview of the recent results and the current status of this formalism from the point of view of quantum gravity. So tensorial group field theories are, in fact, a general framework for peculiar quantum field theories. The defining features of these field theories are the following. So first of all, the field is a tensor, normally on some group domain. And the domain can also have additional components on top of the group arguments. The non-local combinatorial pairing of the tensor field arguments, in particular the ones defined on a group domain, is the other, and in fact the main specific feature of these field theories that distinguishes them from usual local field theories on, say, flat space-time. These field theories are going to be non-local in the pairing of the arguments with respect to some of these arguments of the field, but they can be local on the additional components of the domain. We're going to see examples of both. As a consequence of this non-local pairing of the tensor arguments, the Feynman diagrams have a more involved combinatorial structure compared to usual local field theories, and they are in fact dual to cellular, often simplicial complexes. Now, the general form of the action is very schematic form represented in the slide. On the slide. So you have kinetic kernels and interaction kernels characterizing each model. And again, the main distinguishing feature is that with respect to the tensor field arguments, in general, the interaction kernels are combinatorially non-local. Within this framework, we have a large variety of models. And we're going to see each of them, or several of them, and I will try to explain what is the relation to quantum gravity of these various models. So to give a first idea and a sort of pictorial impression of the main features that I just illustrated of these field theories or these tensorial field theories, I give you just the simplest example. And let's consider a random simplicial tensor model at rank 3. So we have a tensor, which is a map from 3 copies of some finite set, let's say a finite group, to the real numbers. And the interactions are such that the indices of the tensors, of 4 tensors in this model, are combined, are identified following the pattern of combinatorial pairing of 4 triangles glued together to form the boundary of a tetrahedron. So we have 2 cells, 2 simplices, the triangles, forming a 3-cell in their interactions. The partition function, therefore, when expanded in Feynman diagrams, so perturbatively in the coupling constant, generates Feynman diagrams which are by construction dual to simplicial 3-dimensional complexes. So this is sort of the simplest prototype of the non-local combinatorial pairing that I was mentioning, and of the general fact that the Feynman diagrams of these models are cellular complexes rather than just graphs. From this model, one can then generalize in terms of the rank, the domain, can add additional local arguments for the tensor field. There could be additional symmetry conditions, and of course, there could be more involved kinetic and interaction terms. One recognizes immediately the generalization of random matrix models. And this is in fact true for all models in the tensorial group field theory framework. And the interest and the potential uses of this type of models are in fact the same as for random matrix models. First of all, they can define interesting quantum field theories per se, and then they provide a definition of quantum gravity as random quantum geometry, matrix models in 2 dimensions, tensorial group field theories, hopefully in higher dimensions. So let's look again at the different models in this framework. The first class is the broad class of tensorial group field theories for simplicial quantum geometries. So we have the idea of defining quantum gravity as a quantum field theory of interacting discrete sort of atoms of space. Within this class of field theories for simplicial geometry, we can go in increasing complexity from the simplest random tensor models, which are purely combinatorial, to the more involved group field theories, which in fact combine the combinatorics of random tensor models with the quantum geometry coming also from different approaches to quantum gravity. So the connection to quantum gravity is for the random tensor model point of view that they define simplicial quantum gravity in the same spirit as dynamical triangulations, as we're going to see. For group field theories, we have a richer form of simplicial quantum gravity definition, with additional data also being dynamically summed over. But then we have a strict connection to canonical loop quantum gravity and spin-fold models as well. A second main class of tensorial group field theories are simply tensorial field theories on flat space. We're going to discuss them in a second. The interest is that they may define controllable conformal field theories and therefore have a connection to quantum gravity through the ADS-CFT correspondence. Let's look first at random tensor models. So we have, let's consider a general case of simplicial interactions, but with rank D tensors. Again, the diagrams are going to be d-dimensional simplicial complexes because of the peculiar gluing of the tensors in the interaction term. And because there's nothing else than pairing of indices, identification of indices over a finite set, then the amplitudes are purely combinatorial with the expression given in the formula. The first main issue that one confronts in dealing with these models, that was in fact the first issue that blocked progress in the early 90s when these models were first proposed, is how to control the topology of the Feynman diagrams. And here comes the idea of coloring and the extraction of topology from coloring. The key factor is an old result in crystallization theory, which says that a D+1 color graph is dual to a D-dimensional pseudo-manifold. And this prompted the introduction of colored tensor models, the introduction of coloring in tensor models and tensorial group field theories by Razvan Gurau in 2009, but then immediately after by a number of other colleagues and friends. So one way to do it is to color the tensors and maintain these simplicial interactions. You have several tensors, each labeled by a color, with some restrictions on how they can be identified, how can they interact with one another, and which tensor degree of freedom can propagate to which. And an example is depicted in the slide. A second way of introducing colors is instead to have a single tensor, but to color the indices of the tensor. And then I have as interactions the UN invariances that you can generate by contracting tensors along indices with the same color. Following this pattern of contractions, once more, you have D+1 color graphs. So the general point, whatever strategy one chooses, is that the Feynman diagrams of such colored tensor models and tensorial group field theories are D+1 color graphs, and one can control the topology in terms of the colored subgraphs. This allowed one main result, despite quite a lot more results. It was that it was possible to define a Largen limit, which turned out to be dominated by melonic diagrams. So let me explain briefly. The amplitudes for such colored models can be shown to scale with the dimension n of the tensor, with a specific function of the combinatorics of the triangulation dual to the graph, or equivalently of the graph, called the degree, or the Gouraud degree, because it was introduced by Razvan. Then one can see that in the large n expansion, in the large n limit, diagrams with vanishing degree dominate, and one can also show that these correspond to special triangulations of a d-dimensional sphere for rank D models. Careful, however, to notice that the degree is not a topological invariant in dimension higher than 2. So spheres will appear also at higher orders together with other topologies. The same Largen limit allows to resum the melonic diagrams, so the perturbation series, and one finds a critical behavior corresponding to that of combinatorial trees. But the perturbative series can be resummed exactly. And this is quite a remarkable result. On the disappointing side, in a sense, is the fact that melons or melonic diagrams correspond in fact to branch polymers. And this is expected to be a problem from the quantum gravity point of view if these are the dominant configurations generated by the dynamics of the model. However, one has to notice on a positive side that this is consistent with the discrete gravity interpretation of such random tensor models. In fact, the perturbative expansion of such models gives a discrete path integral for gravity weighted by the Regge action on the equilateral triangulation corresponding to the Feynman diagram. Only combinatorics matters, so you can only interpret the path integral as defined on equilateral triangulations, like in the dynamical triangulations approach. And the correspondence is in fact quite simple. You need to identify with the gravitational parameters, Newton's constant and cosmological constant appear in the dynamical triangulations approach. You have to identify with them the parameters of the tensor model, the dimension of the tensor, and the coupling constant. Many other results have been obtained in the last roughly 10 years in the context of random tensor models concerning both the perturbative expansion, but also a lot of non-perturbative results for these models. One main issue is whether one can go beyond the branch polymer regime, the regime of the dynamics dominated by branch polymers. And here there are a number of contrasting results, some encouraging. For example, that some combinatorial restrictions seem to allow to change universality class, but also there are some constraints on, let's say, how happy we should be about these encouraging results. Let's move on to a second class of tensorial field theories with an interest for quantum gravity, those that are simply tensorial field theories on flat space. We are going to see that the results, the combinatorial results of random tensor models do in fact play an important role also in this apparently different context. The initial motivation for this type of models comes from the SYK model, studied by many people. It's a system of n disordered Majorana fermions in 0 dimensions, just time, temporal direction. It is a system very simple, but with interesting properties. In particular, the large n limit, where n now is the dimension of the fermions, is in fact solvable. And it seems to have a conformal symmetry, strong coupling. Moreover, interesting connection to JT gravity has been found, and so it is considered a toy model for quantum black holes, maybe even a simple realization, exact realization of the ADS-CFT correspondence. Very interestingly, as noticed by Witten in 2016, the same large n behavior of tensor models is the one found in this SYK model. And this prompted a conjecture first, and then the establishment of a number of results about a general correspondence between disordered SYK systems and unitary tensorial quantum mechanics. I give you an example of a quantum mechanical system of tensor type. So a tensor model in 0 dimensions with a time dependence in the tensors. And this is the Klebanov, Tarnopolsky, and then Karotsa-Tanasa model. This model has, in fact, the same type of melonic dominance, like the random tensors we discussed earlier at large n, and it has a closed system, a closed Schwinger-Dyson equation for its 2-point functions. And in fact, one can find, again, conformal symmetry, a strong coupling, relation with JT gravity and the effective action of boundary gravitons in JT gravity. And so this suggests that it could be a realization of some approximate ADS2 corresponding to an approximate CFT in 1 dimension. This is the initial motivation that prompted the study of generalized tensor field theory models in flat d-dimensional spacetime. And one example is the one reported here by Benedetti, Gurao, Aribay, and Suzuki. And you see you have a 3 tensor, a rank 3 tensor, with a dependence on d flat directions, local in such d flat directions, but maintaining the non-locality in the pairing of the tensor arguments with combinatorial patterns labeled by these bubble diagrams in the interaction terms. And this is an interesting model because it seems to flow to a unitary conformal field theory in the IR. And once more, the interest in this type of model is that they seem to be controllable at the non-perturbative level thanks to the melonic dominance. And in fact, a number of results have been established. I just mentioned a couple in the next slide. The goal of all this, all the work on this type of models is that, first of all, they may allow us to define SYK-like models in dimension higher than 1. Second, they can give new controllable, non-supersymmetric conformal field theories. And clearly, if that is realized, we are going to have a strict relation to quantum gravity through the ADS-CFT correspondence. A large number of models have been studied, both in the quantum mechanical setting as well as in the proper field theoretic setting. I don't list all the results, but again, the promise of defining unitary conformal field theories seems to be at least partially realized already in the examples that have been considered. The next step in this program, beyond extending the analysis of these models to higher orders, to other features, and to consider even more models, the next step, I would say, is to understand what is the holographic dual of such melonic tensorial conformal field theories. Instead, we move to the other main class of tensorial group field theory models, those for simplicial quantum geometries. The motivation is, first of all, that already extending random tensor models to proper field theories, there is a hope to go beyond the melonic order thanks to a non-trivial RG flow. Of course, a more formal mathematical interest is simply to define non-trivial new constructive quantum field theories. Now, an example of these tensorial group field theories for simplicial quantum gravity, so the field theoretic generalization of random tensor models, is given here. You can consider a field being a map from D copies of U1, very simple abelian Lie group, to the real numbers. You can expand in modes if you want, and the corresponding modes are in fact tensors over a discrete set. And if you put a cutoff, then we have really the modes of the field to be literally the same tensors we discussed in the context of random tensor models. However, we also introduce a differential operator in the kinetic kernel, which becomes, in terms of modes, a multiplicative function of the tensor indices. The general structure is, however, the same. So you have a kinetic kernel now involving differential operators, and then you have an interaction kernel with the usual tensorial non-local pairing of field arguments. Now, most results from random tensor models, from the simpler models we discussed, can be simply extended or just hold true. In particular, the ability to control the topology of the Feynman diagrams and in general of the interactions with this model, this class of models. Then, however, we have proper quantum field theories on a group manifold. So there are more group theoretic tools available. They are going to have non-trivial RG flows and possibly a richer critical behavior. Now, the perturbative amplitudes, if the kinetic and the interaction terms remain very simple, then they're basically the same as in tensor models, so purely combinatorial. But the moment you have additional invariance conditions or on the fields or more involved kinetic interaction kernels, then you may have more involved perturbative amplitudes, in particular with suitable invariance conditions in the fields. One can show that the perturbative amplitudes become lattice gauge theories on the lattice dual to the Feynman diagram, with the gauge group being the one chosen for the domain of the tensor field. One main task is to show that these models are renormalizable at the perturbative level. The strategy is to treat them as standard field theories, one, however, to adapt the standard techniques to the more involved combinatorics of the Feynman diagrams of tensor models. I point out that, for example, to give you just an idea of what it means to adapt things, well, the typical contraction of divergent subgraphs and absorption of the same in effective vertices, from a lattice perspective is equivalent to the coarse graining of the lattice gravity path integral. So there is a corresponding interpretation of the graph operation in terms of the dual lattice. There are many results that have been obtained concerning perturbative normalization of tensorial field theories, and a large number of different models have been shown to be perturbatively normalizable in rigorous terms in different ranks for both abelian and non-abelian groups, compact and non-compact, with or without additional constraints on the fields, and even beyond group domains to homogeneous spaces. And one finds even asymptotic freedom in several of such models. In fact, even more advanced techniques like of-algebra renormalizations has been adapted to tensorial field theories. At the non-perturbative level, there's been a parallel flow of analysis and results, constructive as well as in the context of functional normalization group equations, a la Polchinski, and even more in the context of the, in terms of the Wetterich-Morris equation. Again, a large number of models have been studied, and concerning UV fixed points, one finds again asymptotic freedom or asymptotic safety for several such models. So they are well defined in the UV. The IR behavior, of course, is much more tricky because one has to deal with the problem of having to choose a truncation and then having to extend the truncation. So that has been chosen to have any solid result on the IR behavior. The again, many models have been discussed. The general consensus seems to be that, as in the local case, you need a non-compact domain to have phase transitions. And this can be achieved in the approximation of the compactness scale of your compact group being sent to infinity, or of course directly dealing with non-compact groups. In fact, the local directions that can be added to the models will also change this conclusion. The other interesting result coming from this non-perturbative analysis is that indeed these models can flow out of the melonic sector. And there are a couple of examples of this being in fact the case. We stay within this class of models, but we move to the full quantum geometric tensorial group field theories, usually called simply group field theories, which have been introduced, in fact, very early in the early 90s as well, then mostly developed in the context of spin-foam models and loop quantum gravity. But of course, they have a lot of benefits from being understood properly as tensorial field theories. So the characterizing features of these models is that one adds quantum geometric data to the quantum geometric data and additional conditions on the tensorial group field theory field, on the states, and on the dynamics in order to have a richer geometric understanding of the states, of the observables, and of the diagrams generated by the quantum dynamics. In particular, one uses the quantization of a phase space description of individual simplices in terms of group theoretic data to have a Hilbert space for the simplices corresponding to the tensorial field. And using that, one can first of all have a number of different group theoretic tools, like different representations for the quantum states for individual simplices. And then one uses this building block, the Hilbert space for an individual simplex, to define a Fock space for the whole field theory. And then every observable coming from the discrete geometry of individual simplices has a second quantized counterpart in terms of functionals of field operators. And the simplest example here, just the volume of the total volume of a collection of several simplices constructed from the contributions of each of them in second quantization. Then, of course, the moment one expands in Feynman diagrams the quantum dynamics, so perturbatively, the amplitudes are going to be much more involved, since the action and the data one associates to each building block are much more complex or much richer. That's, if you want, the negative side. On the positive side, the additional structure allows direct contact with other quantum gravity formalism, so more results and more tools. For example, the connection to simplicial quantum gravity is now much richer. The fact is that the Feynman amplitudes are now simplicial gravity path integrals, again for gravity discretized on the lattice dual to the Feynman diagram. But now there are on the lattice additional dynamical geometric data given by the group theoretic variables of the models. So we have, for example, the group elements have an interpretation as discrete gravity connection, and the group representations have an interpretation in terms of spectra of discrete metric data, edge lengths or triangle areas and so on. So we have a lattice gravity path integral on a given lattice with such group theoretic variables, dynamical, complemented by a sum over lattices generated by the perturbative expansion. So we have both the main idea of dynamical triangulation together with the main idea of quantum Rage calculus for simplicial quantum gravity. There is a strict connection of these models to loop quantum gravity as well, because the same, in fact, one has the same Hilbert space of loop quantum gravity states, so spin network states, for each given graph. A boundary graph, if you're thinking of the quantum dynamics. And however, so the point is that you're dealing with spin networks as sort of quantum many-body states, and so you are embedding this Hilbert space on a given graph into the separable Fock space of spin networks in this GFT context. And one is also a second quantized version of the same observables that one would have in loop quantum gravity on a given graph. The differences are in the relation between quantum states associated to different graphs, which are treated very differently in this group field theory context and in canonical loop quantum gravity. Plus, of course, we're dealing with abstract graphs, and there's no embedding into any canonical hypersurface. There is a strict connection to spin-foam models as well that can be seen also as covariant loop quantum gravity dynamics. And the statement is simply that for any spin-foam model amplitude, the Z defined there for a given complex, there is an associated group field theory action that reproduces the same amplitude as a Feynman amplitude. On top of that, the group field theory defines a sum over spin-foam complexes, so it gives non-perturbative completion of the quantum dynamics defined by spin-foam models. That is, group field theory offers new quantum field theory tools to deal with the dynamical combinatorics of quantum gravity states in the sense of loop quantum gravity, but also tools for approaching the continuum limit and the extraction of an effective continuum physics. So most of the results, and in fact all the results associated to given graphs in loop quantum gravity apply equally to the group field theory because of this correspondence. And I just mentioned one set of results, which are all the results that follow either from the just quantum geometry of the theory, which apply equally, but also the ones that follow from the correspondence between spin network states and tensor networks. So renormalization is much more challenging, however, for these models, simply because the amplitudes are much more intricate. So very little is known about both perturbative and non-perturbative renormalization group properties of these models, and I've listed here a couple of results. On the other hand, we have much more control over the geometric interpretation and therefore nice guidelines for model building. I mentioned an example here. One can define models for quantum gravity coupled to scalar matter, which are useful, for example, in the context of effective cosmology that I'm going to close the talk with in a second. I just mentioned the guideline here is that one wants to define a group field theory model such that the Feynman amplitudes are lattice gravity path integrals for gravity coupled to scalar fields. The result of the analysis is that one ends up with a model in which there are no local directions, which are the quantum geometric ones, and local real directions, which are the ones corresponding to the scalar field degrees of freedom. So one gets exactly the type of mixed local, non-local tensorial field theory that was the case for the tensor field theories on flat space. But in this case, we also have dynamical tensor degrees of freedom. So there are a number of other results which I'm not going to discuss at all in the context of group field theory. I put some reference here, and of course, you can read with more calm the slide and ask questions during the panel session. I want to spend the last 2 minutes discussing one avenue towards the extraction of effective continuum physics in this framework, taking advantage of the quantum geometric data and the richer discrete geometric interpretation of group field theories. This is the so-called group field theory condensate cosmology. The main ideas at the root of this line of research are the following. So one considers a condensate phase of the group field theory system. So the idea being the space-time in geometry arise from some group field theory phase transition. Second, one looks for the continuum gravitational dynamics in the context of the hydrodynamics of the group field theory models. Third, one needs to recast the group field theory effective action has to extract an equation for geometric observables using the discrete gravity intuition. Last, one adopts a relational strategy for the definition of temporal evolution as well as local physics. And it's for this that the coupling with scalar fields used as clock and rods is crucial. The general facts that one can show are two. First of all, the domain of the group field theory field, the mean field of the effective action, is equivalent, is in fact isomorphic to the mini superspace of homogeneous geometries. Second, the hydrodynamic equation gives then something that is a nonlinear extension of quantum cosmology. confirming the interpretation in terms of effective cosmological dynamics. Several results have been obtained recently in this context. I mentioned a few. One can show that the effective relational dynamics so obtained has the correct classical limit at large volumes and late times. One finds that a quantum bounce replaces the Big Bang singularity if one stays at this hydrodynamic level of description. One can recover, in fact, a loop quantum cosmology-like dynamics in a special regime of the effective dynamics. And one can control and compute in detail the quantum fluctuations of geometric observables, well, the volume in the isotropic case, the volume of the universe, and they are indeed under control. And this analysis has been first done at the mean field approximation in terms of coherent states of the field operator, but has been also generalized beyond that. Then one can show that generically the group field theory interaction, so the interaction between the building blocks making up the continuum space-time, we know, generate accelerated expansion for the universe, and with appropriate restrictions on the model, but rather generically, one can find that at late times, one has a phantom-like dark energy and an asymptotic de Sitter phase. In order to obtain these last two sets of results, one has to adopt a more phenomenological type approach in terms of how to deal with the group field theory effective action. So the main lesson is that in emergent space-time scenarios, large-scale properties can be the direct result of quantum gravity effects, showing the limitations of effective field theory intuitions. More recently, there's been also a lot of work on extending the framework to inhomogeneities. Results are encouraging, and I'm happy to tell you more if asked. They are encouraging, first of all, because one can recover the classical results in the appropriate regime. The big issue is what if there is a cosmological significance also for the underlying phase transition leading to the condensate phase, to which we gave a cosmological and more generally geometric interpretation. With this question, I thank you for your attention. Thank you.